At this point, we know that a change in flux induces an EMF. And it's important to note that it's the change in flux that induces the EMF, not just a flux itself. And we know that the faster the change in this flux, the greater the EMF induced. So it's time to learn about how to make some specific predictions, or add some numbers to this. So here's our formula for the amount of induced EMF. And let's focus on this portion first. And we note this is a rate. It's the rate of change of flux, dividing by the change in time here. The EMF is therefore proportional to the change in flux, that is, could be the change in magnetic field and/or a change in the area, and the EMF is inversely proportional to the time taken for this change. And this agrees with our demos so far. Now, what's this anode here? In our previous flux calculations, we always assumed a single loop or frame surrounding our area, and that would indicate an N of 1. But going forward, we'll run into lots of examples where there's a bunch of loops surrounding an area, a bunch of wires all wrapped together. And each loop experiences the same change in flux, and the resulting induced EMF is an accumulation from all these loops. So if we have 5 loops, then the accumulated change in flux and the induced EMF is 5 times the result as it would be with a single loop, or N equals 5. For 10 loops, N equals 10, and so on. So lastly, let's consider the negative out front here. And this is simply to help us keep track of the EMF direction. An induced EMF always opposes the change in magnetic flux, and therefore we have a negative. We'll get more into the direction details later, but for now, just remember to write the negative in front as a direction reminder.